Welcome to Scholar Sauce. A couple of months ago, I reacted to Alan Becker's amazing video, Animation versus Geometry, and it is the most watched video on my channel. And there were a ton of people in the comments that were asking me to react to animation versus math, and also the animations versus physics. And so I figured that that's something that we ought to do. So today we're going to react to Animation versus Math by Alan Becker, and in a couple months, maybe I'll react to Animation versus Physics. Now, one disclaimer about this, I did watch Animation versus Math like over a year ago, about the time when it came out. I don't really remember it very well, so hopefully this will be basically like a reaction of watching it for the first time. But yeah, so let's get to it. That's a good number to start with. Yep, equality. Oh, it's nice. Like how he uses the way it looks in order to make it get something new. Yep, if you add all these together, it keeps adding up, as you'd expect. Well, now he's got the arithmetic set up that he could actually set it up to be multiplication too, because he's adding groups of the same number. So I kind of wonder if that's what he'll end up doing. He's got it added to 100. Oh, now he's going to do subtraction. You know, I almost feel like I wonder if this would be like a better way to teach kids about arithmetic. Just let them mess around with a bunch of numbers like this in some kind of computational thing, so they can kind of figure out some patterns on their own and then have them discuss it afterwards. Oh, no, that's funny. It switched to e to the I pi. That's fantastic. So let's go back just a little bit. That's fun. So e to the I pi is kind of an interesting thing. This has to do with how we define the exponential function in complex numbers. According to Euler's formula, e to the I theta is equal to cosine of theta plus I sine of theta. So if you have e to the complex number a plus ib, what you end up getting is the e to the a part will separate out because you're adding the exponents. So you get e to the a times e to the ib, and Euler's formula says that e to the ib is equal to cosine of b plus I sine of b. And so you end up getting e to the a times this cosine of b plus I sine of b. And if you plot that on the complex plane, you get a location in the complex plane where if you take an arrow from the origin and point to that location in the complex plane, you get that the x-coordinate is e to the a times cosine of b, and the y-coordinate is e to the a times the sine of b. And so it ends up being that the e to the a is the length of the arrow from the origin to the complex number that it's pointing at, whereas the theta is the angle from the positive real axis to the number. So the e to the a is referred to as the modulus, or the length of the complex number, and then the b is the argument of the complex number because it's the sort of angle that it makes. And so when you multiply two complex numbers together, you get this e to the a plus ib times e to the c plus id. If you multiply those together, since it's the same base, you get e to the a plus c plus I times b plus d. Now to the e to the a plus c, that separates into an e to the a times an e to the c. So those are the moduluses of the individual complex numbers. And so you end up getting an e to the a times e to the c times e to the I b plus d. So when you multiply two complex numbers, what it does geometrically is it multiplies their lengths together, but then adds their arguments. So you can see sort of like if you take two complex numbers represented this way in the complex plane, if you multiply them together, their lengths get multiplied, and that's the length of the new arrow from the origin. And then you add their arguments together, and that's the product of the two complex numbers. And so this e to the I pi is a really neat representation of this complex number arithmetic and this geometry of it. And e to the I pi, this would be a complex number that has length 1 because it has 1 times the e to the I pi. The argument is pi, and so the angle from the positive real axis is pi, which means that it's pointing now towards the negative real axis. And so this ends up being the number -1 pointing in that direction. And so so that's why when he hits this button, the -1 suddenly shifts into this e to the I pi, and he's going to mess with it. It ends up being what's called Euler's equation, which is a really, really beautiful equation that correctly written is e to the I pi equals -1, or e to the I pi plus 1 is equal to 0. But Taoists will try to tell you that it should be e to the I tau equals 1 because they think that looks nicer. But I personally, I'm in the pi camp on this one because tau would be the second positive argument where e to the I theta becomes a real number. And I think that the fundamental quantity that you should use should be the one that's the first time something happens. And so the first time e to the I theta becomes a real number, with theta being a positive value, is at pi. And so that's actually, to me, the fundamental time that something's happened to this guy here. So I would argue that that Euler's equation is actually a support of pi, not of tau. But you can put down in the comments how you guys feel about that, because there's some strong feelings and all that. Now, I've talked way too much about this e to the I pi, and I'm sure it'll come up more in the video. So I'm going to go ahead and just hit play and keep going. He multiplies it by I, so now it's -I, and so it goes into the imaginary realm. That's awesome, and it disappeared like that. I love it. You know, it makes you wonder, like, does Alan Becker, I wonder what his educational background is like. Is Alan Becker, like, obviously he does a lot of computer animation, but I really want to find out, does he know all this stuff beforehand? I mean, does he research all this stuff in order to make it like work really well? I mean, I wonder what his mathematical background is and his physics background, because I think he has a lot of fun with that. I'm gonna have to look to see if he has like animation versus like biology or other kinds of sciences. I'm kind of curious about this now. Well, he has like 220 videos. Let's see. I mean, if I just scroll down here, he's got animation versus geometry, animation versus physics, animation versus math. I kind of wonder what his educational background is, because yeah, looking at it, it doesn't look like he has any other animation versus science stuff besides just he has the math and geometry, and he has the animation versus physics. I mean, I guess maybe those are kind of a little bit easier to do in this sort of black backdrop stuff where they figure out some cool things. But it's interesting that he picked math and physics to be the ones that he really enjoyed. So I'm kind of curious as to what led him to want to do that. Anyway, let's get back to the video here. So now he multiplied by -1. He's got two different things now. Oh, he's going to turn it into a multiplication symbol. Ooh, I love it. That's great. I love how it just made it into a bunch of sums in different rows and stuff like that. And now he's got division going on where it's iterated subtraction. That's pretty cool. Then it shows why dividing by 0 makes absolutely no sense, because how many zeros can fit into it? That's fantastic. Oh, now we got exponents. That's great too. I go back a little bit here actually. So this is important. So this quantity here, this 6 plus 2 quantity squared equals 64, this is really interesting, because one of the most common errors that people make when they're first learning algebra, in fact, this mistake is so famous, it actually is called the freshman's dream, is the idea that exponents distribute across a summed quantity like this. They don't, but the mistake that students make here is they try to square the 6 and then add it to the square of the 2. So 6 plus 2 squared, just like the distributive property would do, they think that it makes this equal to 6 squared plus 2 squared, or 36 plus 4, which would be 40, which is clearly not what's going on here. So as he goes on here and shows that this is actually still 8 ones added together and then multiplied by how many of those there were. So you get 8 rows of 8 ones. It kind of is nice to show that this is not, what's going on when you try to square a sum. Exponent scores don't distribute across sums, but it's just kind of an interesting error that students make. It's not intentional. I mean, it's just it feels like a natural thing to do when you're not really thinking about what all these different things mean. It's easy to kind of get confused with that kind of thing, almost like a grammar mistake. Anyway, it's just cool that he has this in here, that it kind of shows that if you're paying attention, you can see how it produces this sort of counterexample to that freshman's dream. And there you can see the -4, -2 now becomes that. Oh, that's cool. It turns it into like an array. I love it. So now we're seeing sort of how the exponents mean. Now that's interesting. Then we get this negative. So what's going on with the division? So that's pretty cool that he's brought that in here as to what all these things mean. And then we get radicals. So what's actually really neat about all this is just seeing how like he's done this really fast in a bunch of animations of like how do you mess around with the things and what do they mean. And when I teach the exponential rules to him, I want to help him kind of see sort of where they're all coming from, because I think it helps you remember what the rules are. But it's interesting when you go through this process of just starting with like what an exponent actually means is it's just multiplying how many things that you're multiplying together. So it's like 3 to the 4th power is 3 times 3 times 3 times 3. That gives you sort of a baseline of like, this is what an exponent means. You start developing rules for like numbers raised to positive integer powers, and you see what those rules are. And then what you do is you try to say, okay, well, if we were going to extend this to be like, say, maybe a 0 power or a negative power or a fractional power, the way you end up defining them is you try to figure out what would be the correct way to define this that would maintain all those observed relationships that we have. So for example, we know that a to the m times a to the n, if you think of m and n as positive integers, then this is a times itself m times, and then a to the n is a times itself n times. And so the total number of things you have multiplied together is m plus n of them. And so that's why a to the m times a to the n should be a to the m plus n. Now that proof only works if the exponents are positive integers. So what happens then, let's say we wanted to extend that to allowing 0 to be an exponent. Well, if we want that rule to be maintained, that a to the m times a to the n is equal to a to the m plus n, then a to the 0 times a to the m has to be equal to a to the 0 plus m, which is just a to the m. So that means a to the 0 times a to the m has to be equal to a to the m. So then a to the 0 has to be defined as a number that when multiplied by another number produces that other number. And the only number that does this for everything is the number 1. And so the only thing that makes sense to define a to the 0 to be is 1. Now, of course, that's only if a is not 0 for other kinds of considerations. In fact, the reason why you can't define something like 0 to the 0 to be a number is because there is no single choice of that number that works for all those rules. So there's no way to make it sort of consistent. Anyway, what I love about his little sequence here in animation versus math here is that he actually kind of builds that whole thing up. Like, what would all of those different operations do in order to make all this stuff work kind of consistently? But he just does it so fast that you kind of don't really notice sort of the nuance of what's going on. But that's one of my favorite parts about teaching exponents, is just to see the development of like why you would define those things that way in order to keep those observations that you made about the sort of simplest case continuing to happen. Anyway, I think it's kind of cool. So let's go on here. In fact, he's actually pulled up something here on the square root of 2 that equals this big long mess of a number, which is going to be an infinite sequence. I'm going to comment on this too because this is kind of fun. There's this infinite sequence of numbers that come after this. In fact, this infinite sequence, it goes on forever. It never repeats. This is a property that all irrational numbers have. But it's also something people get like super excited about with pi, that it has like this infinite decimal representation that never repeats. But that happens with any irrational number. In fact, I have a pretty fun video called Stop Saying That Pi is Infinite that talks about how pretty much everything that people cite as being like super cool about pi is actually true about practically every number. And so that's actually not what's cool about pi. And so the video itself talks about like what actually is cool about pi versus all these other things that people kind of get distracted by that are true about almost every other number, including say like the square root of 2 here. Anyway, we'll go on. Oh, now there's that I again. So he took a square root of -1, and he gets back to that I that ran away earlier. Oh, now that's interesting. So now he's kind of messing around. Oh, there's the e to the I pi again. He's going to chase it. Oh, it's like a monster. Or a dog, I guess. I don't know. That's right, get him. Oh, did you... Hang on, wait, go back. Just see him do that? I'm gonna go back just a tiny bit. This is actually really cool. When he attacks the beast here, for a second as he's messing with it, the e to the I pi turns into Euler's formula. Let me see if I can pause it at the right moment. So that's e to the I pi as it's separated out into Euler's formula. So e to the I pi is cosine of pi plus I sine of pi. The negative, of course, was just the negative that was in front of the e to the I pi earlier. But that's how it pops out. Isn't that neat? Like he just throws that in there for just a split second. You'll miss it if you aren't paying attention. Anyway, let's keep going. He threw his negative sign at him. Oh, that's cool. Okay. Oh, gotta go back. Okay, so when he subtracted the pi there, it goes back to e to the I 0. Now remember that number after the I in the exponent is the argument. So it started at negative pi, which is over on the negative x-axis. Well, I guess from your guys' view, that'd be like over here. And then when he hits it and it subtracts the pi, it makes him go to e to the I 0, which is flips him all the way back to a 0 argument, which is the positive x-axis, and that's how he gets away. That's awesome. Just a beautiful way, super fun way of showing that geometric stuff that I was talking about earlier. Multiplied himself so he goes faster. Tried to make him negative. That's right. I love the ones here. Now it's all like sort of Minecrafty again. Got an axe. Oh, he's created a bow and arrow out of it. Oh, did you see that? E to the I pi fourths. So again, that pi fourths is the argument, so it pops him up to like a 45-degree angle and he keeps going. He's shooting fours at him like arrows. That's awesome. Oh, now he just used the I to get up that high too. What's this dot? Oh, it's the imaginary axis. That's great because it's the dot on the I. But when it goes that way, it's the real axis. So now we're actually going to see the geometry of the complex numbers. When he throws it the other way, it'll make a negative number. Look at that. There you got the unit circle and the complex numbers. All the way down, all the way to... That's weird. So what that's describing, of course, is that a radian, right, is the angle measure that sweeps out a radius worth of arc length. Now, the circumference of a circle is 2 pi times the radius. And so there have to be 2 pi radians of length around that. Instead of being exactly 6, that ends up being 6.28 or tau. Radians all the way around. That's actually the main reason why people like the number tau, is because it's the full number of radians around the circle. Anyway, so that's what he's depicting here, but of course it's doing it in sort of complex numbers. But you can see that the complex numbers are actually like mirroring that geometry and stuff because they behave that way. Nope, there's the radius r. So he increases the radius r. Of course, the circle gets bigger, so now we have like, I don't know, what does it look like? 5? Like 5 is not exactly 5, but that's where the R on it's going. Oh, it was 5. If you add 2, it becomes 7. And 3. Now the r times theta here, right? So he's moved the theta all the way around to get 2 pi. And so the r times theta is the length of the circumference here, right? So it's the arc length. And since the theta right now that he had it set was all the way around 2 pi, the r theta is the entire circumference of the circle. But if he messes around with this angle, I'm suspecting that it'll probably reduce it down to a smaller arc length. That's funny. There you go. Yeah, so he's messing with the size of the angle, and that's telling you how much arc length it produces. But it doesn't matter what the size of r is, it's still going to produce that. And so as he rotates it around, he gets pi, because that's where that first occurs. You have a cosine and a sine, the two parts. The sine is the y part. Okay. So the sine measures the height as you go around it. It measures the y-axis or the imaginary part, depending if you're talking about this as being in a complex plane or not. And so if you watch this, it's actually really cool. You can see it track the y value of where the dot is as he hits it with the sine. So this will track the height of it. Do you see that? It's tracking how high the thing is, and that's producing that wave. Now when he hits it with the cosine, it's probably going to go up because it's going to track now the x position, the coordinate along the x-axis, or the real axis if you're doing it in complex numbers. Yeah, so you can see that. It's exactly like I expected. So it's producing a wave function that's doing the same thing, it's just tracking the x-coordinate. So when you hit both of them, now it's tracking both things. And you can see how it's picking up both those things at the same time. And then when he makes it I sign, that's going to pull it up and move it to the top, I guess. And now you get this kind of fun little double helix. When he adds them, you get e to the I pi. There it is. Get him. Oh, I gotta get that off so we can see that. Oh. I gotta go back. That's funny. Okay, so this right here is an infinite series that's equal to the exponential function. E to the x is equal to the infinite sum from n equals 0 to infinity of x to the n over n factorial. This is the Taylor series of the function e to the x. And so if you put whatever you want into an x, this converges for all values. So e to the I pi would be the sum of I pi to the n over n factorial. This ends up being a series representation of that function for that value at I pi. So this is a Calc 2 concept. It's really cool. So now he's got this, and it looks kind of like a bow and arrow, so he's going to start launching things at him. It's pretty fun. Or some kind of gun, I guess. Maybe not a bow and arrow. What is it? He's shooting. What is he shooting at him? What is he launching at him? Oh, I think he's launching I to the pi, I pi. Oh, that's cool. Okay, we got to go back. This is way more subtle than I thought. So what he's done is when he shifts himself into the infinite series, what he has now is he has a whole bunch of I pi's to the n over n factorial, and he has an infinite number of them. So what the gun's actually shooting out is values of the I pi to the n over n factorial. And each time he launches it, it's a different exponent, a different value of n. And if you watch, the n equals 0 increases because he's losing that as he shoots it. So watch him fire. You'll watch the n equals 0 on the bottom of this sum will change. You see that? Because he launched the 1, the 2, 3, 4, 5, 6, 7, 8, 9. And see, now he's at n equals 9. Launched another one, there's 10, 11, 12, 13. So he's launching those pieces at different values, but he has an infinite number of them, so he'll never run out. That's just a really clever use of what an infinite series does. He's never going to run out of ammo launching those things at him. Although one could argue that actually the value of each of those things is getting significantly smaller as he goes, and so the strength of each successive bullet is probably less explosive because the value is smaller. I don't know. Maybe that's too nerdy. So he's created this circle, 8 pi r squared. Let's go back. I think that was the volume of the cylinder. So he used this. He's going to 8 times the circle, which will give us a cylinder that's 8 long. 1, 2, 3, 4, 5, 6. Yeah. So pi r squared, of course, is the area of the circle, and the 8 times it is the length of the height. So this is the volume of the cylinder. 8 times pi r squared. That's pretty fun. Just love these like subtle things. So well thought out. So he jumps in here, he throws the r over there. Now if you remember, e to the I pi, of course, is just -1. So if the e to the I pi being -1, this is just equal to r plus theta. That's where that's coming from. He's spinning that, making it really large. Include him in there. Multiplied himself by -1 to get to the other side. Multiplying, of course, by -1 changes the sign of everything. But if you're over on the negative real axis and you multiply by -1, that's going to pop you over to the positive real axis. So by hitting himself with the negative, he jumped to the other side of the circle. That's pretty cool. Oh, there he is again. Okay. Okay, now this is great. He's going to multiply himself again. So this formula here, if you look at it, if you're familiar with the hyperbolic functions, this actually looks very similar to that. The hyperbolic sine is defined as e to the x minus e to the negative x over 2. And the hyperbolic cosine is e to the x plus e to the negative x over 2. Now, that's what you get if you put real numbers in for the x values. If instead you put these imaginary numbers in, you actually get the regular trigonometric sine and cosine. So sine and cosine are defined almost the same way as the hyperbolic sine and cosine. It's just they have to include imaginary numbers, this I here, in order to make it work. So what you have here on the left is the cosine of pi written in that e to the I pi plus e to the negative I pi over 2 form. And then on the right, you have a sine. That's why there's an I on the bottom. Anyway, so that's kind of where those values come from and what they're doing with here. But really what it does is it gives him a couple of extra e to the I pi's that he can throw at him. And there's more of them. Just another way you can get a whole infinite number of them. Now I just love it. So you had sine over cosine, that's the tangent. Now he's got this like function gun. Oh my gosh, I didn't even notice that. I gotta go back. That's pretty cool. Okay. Everything in this is so subtle. This is a tangent function, right? So sine of x over cosine of x. That's how we created it. I'm going to go back just a little bit so you can see that. All right, so he's got 9 times the sine of dot over time, and it makes a tangent thing. So now he's got this tangent function that is going to create this gun. He cocks it, and as he shoots, watch what happens as the bullets go through. Watch what it displays as it goes through the line. You see that? Those little lines there, that is the graph of the tangent function. So he's got this tangent graph that's being plotted each time he fires this gun. That is serious attention to detail. That is really, really cool. Blink and you miss it. Of course, the real funny thing about all this is that he's being chased by a bunch of imaginary friends, so this is like all in his head. He just keeps increasing the R. Oh, multiplied it by pi, which moves him around. Even more of those gunships. Yeah, I don't think that's going to be enough. If you notice, each time he shoots them, each time he kills them, he zeroes them out. Like, that's how he's defeating them. He's multiplying them by 0, basically, and to zero them out. That's great. It's an infinity gun. So this infinity that he's multiplying them by is giving this, it's like an asymptote. That's what it's killing. Oh my gosh. Did you see that? That was awesome. Okay, so he's building all this stuff out of the E stuff. He's going to shoot another infinity, which is shooting like an entire set of asymptotes around. Each of the zeros of the tangent function is what was hitting the E's to zero them out. But now he's going to stop that. He's going to add up an infinite number of them, and it's going to produce a limit here. Watch this. Okay, so he's going to shoot that. He breaks it up. Look, it's getting a limit here. It goes all the way limit as x goes to infinity. So he's got this limit as x goes to infinity. If you put all that together, boy, I just realized there's so much stuff that's going on here. He's got like logs of 1 minus I, like just any representation of this stuff that you can have. That's really cool. But this limit as x goes to infinity of adding a bunch of things. When you add up an infinite number of infinitesimal things, you get an integral. And that's why you get this limit thing that's happening. You end up getting this integral sign. Integral from 0 to infinity of all the e to this stuff. It's kind of cool. So we're really throwing in some calculus here. It's fun. Who knew that math could be so dangerous? That moves himself up by 9 by adding 9i. And keep going up. Get him, guys. He's moving one at a time, each direction. Now he's shooting the entire array of cosine of I plus I sine theta. My gosh, he's just hitting it. That's great. Wow, that's awesome. Oh, and he still gets away. It's like, no, you don't. Oh, he went into the imaginary realm. Oh my goodness. He's now in the imaginary. Oh, and he let it through. All these square root of negative numbers because they're all imaginary numbers. That's fantastic. We're going to get a Mandelbrot set. I think that's what this is going to be. If I had to take a guess. Ah, maybe not. We'll see. Oh, he put himself back in the real world. Shattered reality. Let's be friends. Let's not destroy the mathematical world. I'm not sure what he's trying to mime to him. So I to the fourth is 1, so it just pops him back where he is. Even the I pi halves, so he goes up vertically. That's great. It's like an elevator. Oh, here we go. We've got so here he's brought in the gamma function. The gamma function has to do with how you analytically extend the factorial. But anyway, it's pretty interesting thing that he has here with this sum here. With the gamma function involved. It's pretty fun. Keeps adding values to it to give more and more of these spheres. And turn it into imaginary. E to the I pi equals -1. And there it was, Euler's function. And now he sent him away. Zeta function and phi and delta. Oh, aleph not. That's great. Man, that was fun. That was just excellent. Alan Becker just, man, top notch. It's the incredible amount of research that he has to do in order to like get this stuff together. And it's not just that, like he's got to go through like just a ton of different mathematical ideas and math concepts and then, you know, distill them down into something interesting that he can tell a story about. It is absolutely astounding. This guy is a master of this stuff. I'm really looking forward to watching animation versus physics, but I will hold off watching that now so that we can do another reaction video later. Thanks for watching. If you're not subscribed to Scholar Sauce, please do so now. It really helps. We've actually been making a lot of progress. We're getting pretty close to 2,000 subscribers at this point. But I hope you guys enjoyed this as much as I did. I'm even wearing a Scholar Sauce t-shirt, so we really want you to be a part of the Scholar Sauce community and make this such a great place to just have some fun and learn about math. And that's it for today. We'll see you guys next time on Scholar Sauce.